Just heard, a rheometer has two essential test modes, speed control and torque control. Tests where the speed or shear rate is controlled are called CSR tests, for controlled shear rate. We control the shear rate and we measure the shear stress. With this CSR test, certain process conditions can be simulated, like spraying, pipe flow, or painting. Alternatively, tests where the torque or shear stress is controlled are called CSS tests, for controlled shear stress. The CSS test is the classic method for measuring dispersions, gels, and pastes. In a way, controlled shear stress reflects the natural way of all things. Any motion is a reaction to an acting force. Our heart pumps blood through our bodies, gravitation pulls rivers and glaciers down into valleys, wind forces waves to travel the ocean. All of this is controlled shear stress in motion, right there for you.
Now have an impression of how rotational rheometers are set up and used for tests. As the next step on our journey, let's take a look at the actual output of rotational tests. How are results represented? How can we actually read a liquid's flow? Let's leave Principal Park, hop into Joe Flo's vintage car, and churn into Curveland.
Our round trip now leads us into long and winding roads. Welcome to Curveland. With curves, you never know what's coming. They go up and down, left and right. There's always some kind of development. This is why rheological results are always curves. Because we are observing the development of a material's viscosity under changing shear conditions.
First off, we need to decide how we want to change the shear conditions during the test. This is our measurement preset. Expressed in a function, such presets resemble step-like ramps, with time on the x-axis and the controlled shear parameter on the y-axis. Remember, we either control the shear stress or the shear rate. If we perform a CSR test, for example, a rheometer usually starts at a shear rate or rotational speed of 0. Then, the shear rate is gradually increased one step after the other, right up to a maximum over a defined period of time. This clear straight preset is what we control. What we can't control, what we want to find out, is how the viscosity of the sheared liquid will change under these defined conditions. So hold on tight. We might be in for a slightly curvy ride.
We get two results from a rotational test, flow curves and viscosity functions. Let's assume we are measuring a Newtonian liquid, like water, in a rheometer. Perform a CSR test, so our measurement preset looks like this, with the shear rate, gamma dot, gradually increasing over time. Now, flow curves are generally plotted with tau on the y-axis and gamma dot on the x-axis. These preset shear rate values, we measure certain shear stress values, and these form the flow curve. In this case, the curve is pretty predictable. Why? Well, let's take a look at the second type of result, the viscosity function. On each flow curve, we have several measuring points. gamma dot 1 results in tau 1, gamma dot 2 results in tau 2, and so on. Now we use these values to calculate viscosities. Tau 1 divided by gamma dot 1 gives us the first viscosity value, eta 1. Tau 2 divided by gamma dot 2 gives us eta 2, and so on. If we note all these viscosity values in a function, with gamma dot on the x-axis and eta on the y-axis, we have a so-called viscosity function. What we see, in the case of water, is a straight plateau. The relation between shear rate and shear stress apparently has never changed, so the viscosity value is always the same. Why? Well, water is a Newtonian liquid. Its viscosity never changes, as we can clearly see in its viscosity function. Let's drive up to the Stir-Fry Inn for some lunch. I actually know the 3 cooks there. This is the situation in the kitchen. Primus, Secundus, and Tertius are currently preparing sauces and dressings. Tertius just had a little accident while mixing a sauce. He spilled a huge pile of starch into his pot of water. This gave me an idea for a little experiment. Primus has a bowl of salad oil, Secundus has a bowl of yogurt, and poor Tertius has his, well, let's say, highly concentrated starch dispersion. They have all agreed to a stirring contest. Who will manage to stir his liquid the longest? There is a catch, though. They all have to gradually increase their stirring speed, just like a rheometer would. 3 shearing chefs have now started to stir. Below, we can picture a viscosity function for each of these materials, which we can check to ensure a fair contest. These materials' viscosities may change, so different amounts of shear stress may be required from our chefs. So far, they're doing good. Now, shear faster. Primus doesn't seem to care. The increased speed doesn't seem to cause him more stress. Faster. Look at Secundus. He's actually smiling more than before. Could it be that with increasing speed, the stirring's actually getting easier? And faster. Oh dear, look at Tertius. He looks like he's going to explode. Let's look at the viscosity functions. Faster chefs. Primus salad oil shows no change. Look at Secundus yogurt. It seems the viscosity is going down. Faster chefs. Tertius starch dispersion. Oh, it's actually going up. The more he's shearing it, the thicker the stuff seems to get. I hate to say it, chefs, but increase your speed once more. Primus seems, well, bored. Secundus seems even happier than before. Hang on, is he reading the newspaper now? And Tertius is not doing good, to put it mildly. Ah, his spoon broke. He's the first one out. Primus stops now too. He's yawning. This may just have become too boring for him. So, Secundus has won this game with yogurt.
Now, let's take a closer look at what happened here. Primus salad oil. What kind of liquid could this be? judging from its viscosity function? Exactly, a Newtonian. He could have stirred it countless times faster. It would have always maintained the same viscosity. We call this ideal flow behavior. Secundus yogurt, on the other hand, shows a declining viscosity curve. The viscosity was decreased. The yogurt got thinner and thinner. This is an example of complex flow behavior. Yogurt is a so-called shear thinning or pseudoplastic material. The more it is sheared, the thinner it gets. Shear thinning materials are all around us, like right here in this restaurant. Ketchup or mayonnaise, for instance. Tertious material, this highly concentrated starch dispersion, also shows complex flow behavior, probably the most exotic of the three. This is a shear thickening or dilatant material. Looking at the teacups here, another example comes to mind. Highly concentrated ceramic suspensions are also shear thickening. All three kinds of flow behavior are caught up and analyzed by rotational rheometry. If Tertius had a rheometer, he would have known which material he was dealing with, and maybe he would have used an iron spoon. But anyway, he didn't sacrifice his spoon for nothing. We have now seen liquids' rheological behavior in action. After a good lunch at the Stir Fry Inn, Joe Flo is off to clean his teeth. We don't usually think a lot about cleaning our teeth. We just do it. Because what could possibly go wrong? Well, there's one thing that could flow wrong, namely toothpaste. How do we generally want our toothpaste to flow? We want it to flow out of its tube, but only at our command, because we need to dose and apply it to our toothbrush. That's why toothpaste needs to have a yield point. What is a yield point? Well, it's a measure of the force required to make a substance flow. Some materials don't flow immediately when sheared, due to their inner texture. They are more stubborn than others. They don't yield straight away. Only after a certain point, their yield point. This effect is mostly found in highly concentrated dispersions and gels, for instance, in lipstick, sealants, or toothpaste.